Have you ever looked up at the night sky and just thought, whoa,
Yeah.
where did all of this come from?
But what if I told you that it might have come from absolutely nothing?
Yeah, today we're going to take a deep dive into that idea. The idea that the universe might have come from nothing. We're going to be exploring quantum physics and how it might help explain, the origin of everything. And you don't have to be a physicist or anything to follow along. I promise we'll break it down together.
It's a question that's puzzled people, for a really long time. Like even ancient creation stories, like we see in the Bible, grapple with this whole idea of nothing. It talks about, creation of heaven and earth, but it doesn't tell us anything about what might have come before that.
Yeah, that's a really good point.
Yeah.
It's like it just kind of starts there, doesn't it? So for this deep dive, we're checking out a YouTube video called Was the Universe Born from Nothing? And it's from a channel called History of the Universe.
It's a really interesting one.
Yeah, it looks at some really complex ideas. We'll highlight the most interesting ones for you.
Yeah, so the video starts out by reminding us that kind of our current understanding is that there was a beginning, like a fiery birth about 14 billion years ago.
Okay.
And we call that the Big Bang.
Right.
And it wasn't like an explosion in space, like we might picture it. It was the expansion of space itself from like this incredibly hot and dense state.
Okay, so we're already dealing with some pretty hard to grasp concepts here.
Yeah.
But then the video just throws in this kind of crazy question. What if the universe came from nothing?
Yeah.
I mean, how is that even possible?
Well, that's where quantum physics comes in. You see, it's a realm where our everyday experiences, they kind of break down. It's a world ruled by probabilities, not certainties.
So instead of nice, neat, and tidy laws, it's all a bit fuzzy.
Yeah, exactly. Imagine trying to pinpoint like the exact location and speed of an electron that's orbiting an atom. You can't, it's like trying to grab smoke. The harder you squeeze, the more it slips through your fingers.
Okay, now that's a visual I can get behind.
Yeah.
Is that where the uncertainty principle comes in?
Yeah, you got it. There was a physicist called Werner Heisenberg,
Okay.
and he's the one who figured this out. And funnily enough, his hay fever played a role in his discovery.
Oh, really?
Yeah. So he was struggling with the math of the atom, and so he went to this tiny island called Heligoland to kind of clear his head.
Okay.
And that's where it hit him. You can't know both an electron's position and momentum with perfect accuracy. The more you know about one, the fuzzier the other one becomes.
No, so it's like there's a fundamental limit to what we can know about these tiny particles.
Exactly. And this fuzziness, it has some pretty mind-blowing implications.
Yeah.
It means that even seemingly empty space, it isn't truly empty. It's like this seething quantum vacuum where these virtual particles pop in and out of existence.
Wait, so nothing is actually a bubbling cauldron of particles appearing and disappearing?
Pretty much, yeah. They're borrowing energy from the void for just the briefest of moments.
That's wild.
Yeah, and this quantum weirdness, this idea that nothing is truly nothing, it might hold the key to understanding, how the universe could arise from, nothing.
Okay, so I'm starting to see how this all connects. So quantum mechanics could explain the birth of the universe, but how does it play out in the grand scheme of things? Like, what about stars and galaxies?
Well, that's what's so fascinating about this. Quantum mechanics isn't just some abstract theory. It's woven into the very fabric of the cosmos, And to really see this in action, the video takes us on this journey from the heart of stars to the vastness of space itself.
Well, I am ready for that journey. Let's start with something a little closer to home, shall we? Our very own sun.
Yeah, sounds good.
Yeah.
The sun is a perfect example of how quantum mechanics shapes the universe, For centuries, people wondered what fueled its immense energy. I mean, it's a giant burning ball of gas.
Yeah, I remember learning in school that it all comes down to nuclear fusion. Well,
Yeah.
where does quantum mechanics fit into all that?
Well, fusion is basically the process where lighter elements like hydrogen are smashed together under immense pressure and heat, form heavier elements like helium.
Okay.
And this process releases an incredible amount of energy, which is what powers the sun.
Okay, that makes sense. But I also remember learning that, atoms have a positively charged nucleus.
Right.
So wouldn't those nuclei just repel each other, making fusion impossible?
You're absolutely right. If we only considered classical physics, the sun shouldn't be shining.
Oh.
The temperatures at its core are incredibly hot, but not nearly hot enough to overcome the electromagnetic repulsion between those hydrogen nuclei.
So how does fusion actually happen? Does quantum mechanics bypass those forces somehow?
Yeah, it does. And it all comes down to that fuzziness that we talked about earlier.
Okay.
The uncertainty principle means that those hydrogen nuclei, they're not at a fixed distance from each other. They exist in this fuzzy state of probabilities.
Right.
And in some of those probable states, they actually get close enough for the strong nuclear force to take over, which binds them together and releases energy.
So it's like they're tunneling through that barrier of repulsion.
Exactly. We call it quantum tunnel.
It really is like a tiny machine working at the subatomic level.
It is. And without it, stars wouldn't be able to shine.
Wow.
We literally wouldn't be here without this quantum quirk.
That's incredible. It just makes you appreciate how these tiny, almost invisible processes end up shaping the universe that we see. But what happens when these stars eventually die?
Well, that's another area where quantum mechanics plays a crucial role. It's all very dramatic, actually. We need to talk about supernovas, the spectacular deaths of massive stars.
Ooh, I'm ready for some cosmic firework. Tell me more.
All right, well, supernovas are fueled by this tiny elusive particle called a neutrino.
Okay.
And neutrinos are so weakly interacting that they can pass through light years of lead without hitting anything.
Seriously?
Yeah.
So if I had a lead shield, like a light year thick, these neutrinos would just zip right through.
Pretty much. Yeah, they're like cosmic ghosts.
Wow. Okay. But even ghosts can pack a punch, right?
That's right. During a supernova, a dying star collapses under its own gravity,
Right.
squeezing electrons and protons together.
Okay.
And this creates a flood of neutrinos.
Okay, but how do these ghostly neutrinos cause an explosion? I mean, they barely interact with anything.
Well, it's true that they rarely interact, but the sheer number of neutrinos that are produced in a supernova is astronomical.
Oh, wow.
And they bash into the collapsing core of the star, transferring enough energy to actually reverse the collapse and blow the star apart.
So these tiny, almost invisible particles have the power to rip apart a giant star. That is truly mind-blowing. But what happens to all this stuff that gets blown out into space?
Well, this is where it gets really cool. Supernovae are like giant cosmic recycling plants.
Okay.
They scatter the elements that were forged in the heart of the star back into space.
Elements like carbon, oxygen, the stuff that makes up us.
Exactly. Supernovae seeded the universe with the building blocks of planets and ultimately life. Without them, we wouldn't have the diversity of elements that are needed for a world like ours.
Wow. So we really are stardust, like they say. It's amazing to think that these quantum processors are responsible for life itself. But this video goes even bigger, right? It asks if the entire universe could be a quantum object.
Yeah, that's right. We've gone from atoms to stars, now we're zooming out to the entire cosmos. It begs the question, could the universe itself be governed by quantum principles?
Okay, now that is a truly wild thought. How could the entire universe be a quantum object?
Well, in quantum physics, we can describe the state of multiple particles using a single wave function.
Right.
It encapsulates all their possible states. So the video suggests that perhaps the entire universe with all its matter and energy could be described by a single universal wave function.
A wave function for everything.
Ah.
So every possibility, every outcome, all wrapped up in one equation.
It's a mind-boggling idea.
Yeah.
And it leads to even wilder possibilities like the many worlds interpretation of quantum mechanics. Have you ever heard of that?
Yeah, isn't that the one where every quantum measurement creates a new universe? So there's a universe where I'm a famous musician and another where I'm, well, still hosting this podcast.
Exactly. It's a controversial idea, but it's taken seriously by some physicists. Even Stephen Hawking explored the idea of a quantum universe where time itself was fuzzy and indistinct.
So if we apply quantum thinking to the very origin of the universe, could the Big Bang itself be a giant quantum event? Could the universe have just popped into existence like a subatomic particle?
That's precisely what a physicist named Edward Tryon proposed back in the 1970s. He suggested that the universe could be a massive quantum fluctuation from a state of zero total energy.
Okay, my mind is officially blown. But if the universe came from nothing, where did that nothing come from? What was there before?
Those are some of the biggest questions in cosmology, and they are questions that Edward Tryon's hypothesis doesn't quite.
It seems like every answer in quantum physics just leads to more questions.
Yeah.
But I have to admit, the idea that the universe could be a quantum fluctuation, incredibly intriguing.
It is, and to kind of wrap up our exploration of the cosmos, the video takes us to the very end of the universe.
No.
Trillions upon trillions of years in the future.
All right, let's fast forward to the end of the universe.
Well,
What's in store for us, or rather, what's in store for whatever's left?
oh, it's a pretty bleak picture, to be honest. Star formation has ceased, and even the longest-lived stars, those tiny red dwarfs, have burned out. All that's left are stellar remnants, white dwarfs, neutron stars, and black holes.
Like a cosmic junkyard of burnt-out stars? It's kind of an depressing thought, but also a little bit poetic in a way. I guess even in this final act, quantum mechanics is still running the show.
Oh, absolutely.
Okay.
Let's take white dwarfs as an example.
Okay.
These are the dense, Earth-sized cores of dead stars, like what our own sun will eventually become.
Right.
And you'd think that gravity would just crush them into oblivion, but something prevents that.
And that something is quantum mechanics.
You got it. It's a quantum rule that prevents electrons from being squeezed too tightly together.
Okay.
We call it electron degeneracy pressure. And it creates this outward pressure that counteracts gravity.
So these white dwarfs are locked in this quantum stalemate with gravity forever.
Well, forever is a long time. Some theories suggest that even protons, the building blocks of atomic nuclei, might eventually decay.
Okay.
This process would take an unimaginable amount of time, like 10 to the power of 36 years.
Whoa, my brain can't even comprehend a number that big. So if protons decay, does that mean all matter eventually dissolves, even these white dwarfs?
It's a possibility, although it's highly speculative.
Yeah.
If proton decay does happen, even white dwarfs and neutron stars would eventually disappear, leaving behind a universe of just subatomic particles and radiation.
Okay, that is a pretty wild thought. It's almost beautiful in a way, but also kind of terrifying. What about black holes? I thought those were supposed to be inescapable, the ultimate cosmic vacuum cleaners.
That's what we thought until Stephen Hawking came along and showed that even black holes aren't immune to the laws of quantum mechanics.
Hold on, how can anything escape a black hole? Isn't that kind of their whole thing?
Well, it all has to do with those virtual particles popping in and out of existence near the event horizon, the point of no return around a black hole.
Right.
Sometimes one of those virtual particles gets sucked into the black hole while the other one escapes.
Okay.
And this escaping particle steals a tiny bit of the black hole's energy.
So black holes are slowly evaporating because of these quantum fluctuations, like they're leaking energy back into the universe.
Exactly. We call it Hawking radiation.
Okay.
And it means that even black holes have a finite lifespan. Eventually, they too will disappear, leaving behind nothing but a faint whisper of radiation.
So at the end of everything, it's just a sea of particles and fading radiation. It's a strange picture, but there's a kind of elegance to it, wouldn't you say?
I think so. It really highlights the profound influence of quantum mechanics on the universe.
Yeah.
From its fiery birth to its ultimate demise.
This whole deep dive has really shown just how much we don't know about the universe. But I guess that's part of the beauty of it, right? There's always more to explore, more mysteries to unravel. And who knows what mind-blowing discoveries await us as we delve deeper into the quantum realm.
Absolutely. It's a vast and mysterious universe out there. And as we've seen today, quantum mechanics plays a central role in shaping it from the tiniest particles to the grandest cosmos.
It really puts things in perspective, doesn't it?
That's it.
It reminds us that we're all connected to this grand cosmic story, that we're all made of stardust, governed by these incredible laws of physics. Humbling and a little bit awe-inspiring.
I couldn't agree more.
And that brings us to the end of our deep dive into the quantum origins of the universe. We hope you enjoyed this journey through time and space. And if you want to explore these ideas further, we encourage you to check out the source video, Was the Universe Born from Nothing?, on the History of the Universe YouTube channel. Until next time, keep looking up and keep asking those big questions.